In Chapter 0, we're going to review things we should probably already know about sets and functions from Math 180 or potentially from other math classes as well. Section 0.1 has to do with a review of sets and subsets. So as a quick reminder, a set in mathematics is just considered any collection of objects. So those might be numbers, but they might be other objects as well, including other sets. As an example, we have the set A, which I've defined here to be the set containing elements 2, 3, 6, 8, and 11. Now, we usually use capital letters when we're describing or naming a set. If we're talking about a set that comes up very frequently, then we might give it a special symbol. For example, for 2 and 3 here, we use this fancy N and a fancy Z to represent the set of natural numbers and the set of integers, respectively. So these are infinite sets. The first one is the set of the natural numbers. Those are your positive whole numbers. We call this the set of natural numbers. And in the second case, we have Z is the set containing 0, as well as positive and negative 1, positive and negative 2, positive and negative 3, etc. This is the set of integers. As we said, a set doesn't have to consist of only numbers. It can consist of other things as well. So we can think of this set of the people in the class that can be considered a set. And finally, in this last case, we have a set of curly brackets with nothing inside. So this is a set whose elements are just, well, nothing. They don't have any elements. We call this the empty set, and sometimes we use the notation of 0 with the slash through it when we're talking about that particular set. So it's called the empty set. Okay, notice that the empty set itself, the set with no elements, we can express it as a 0 with a slash or as a set of curly brackets, but we don't want to describe it as 0 with a slash with curly brackets around it. So this is the empty set. But on the other side of the inequality here, this is a non-empty set. This is a set that has one element. That one element happens to be the empty set itself. So just be careful when you're dealing with a notation here. All right. So a couple of other things to note about notation. We use this symbol here. We should highlight it when we're talking about whether something is an element of a set. So 3 is an element of the set A because I see it listed here as an element up above, but 4 is not an element of the set A. So we use that same symbol with the slash through it to say not an element. And also note that an element is different from a set. So, for example, if you have a set or curly brackets with a 1 inside, that's not the same as the number 1. This is a set. The number 1 on its own is not a set. It's a number. All right, so just be clear when you're trying to describe a set, it should have curly brackets around it, or sometimes you're giving it a specific name, and that's okay. You could say something like A, as long as it's clear that that A is actually equal to a set and is not just a number. Now, there's lots of different ways to write out sets. So, for example, the set containing 1, 2, and 3 is the same as the set containing 2, 3, and 1, and it's the same as the set containing 3, 2, and 1. And the reason for this is just that the order does not matter in a set. The order that you list the elements doesn't matter, right? So what makes sets equals is whether or not they have the exact same elements. And these 3 sets that we've listed have the exact same elements, so the order that you list those elements doesn't make a difference. Another thing to know about sets is that we often use ellipses, those are your dots right here, to indicate a pattern. And so you could write something like this set here, which looks like the set of all even natural numbers that are less than or equal to 20. We could describe this as 2, 4, 6, 20. Right? It's clear what this pattern would be, that it's going up by 2 every time. And so it's just a shorthand way of expressing a pattern. Not all sets can be described using dots. If we go back to this last page and look at the set A that we had seen before, there's not really a good way to describe that set using ellipses because there's no particular pattern to the elements in that set. Okay, so Other ways of describing sets, oftentimes in math, we'll use something called set builder notation. Set builder notation is a way of describing a set based on some property that all the elements in that set have in common. So as an example, if we look at this set here, it looks like all of the integers between -12 and 9. We can describe this in set builder notation by saying exactly what I just described, right? This is a set of all integers. So we can say this is a set of all x in the set of integers. That's what this notation means. X is an element of the integers. Then we use a semicolon to mean such that. And, well, what do all of these numbers have in common, aside from the fact that they're integers? Well, they're somewhere between -12 and +9, including those endpoints. So we could describe this in set builder notation as the set of all x in the set of integers such that x is between 9 and -12. So this is one way of describing this set in set builder notation. It's not the only way, but it's one way of doing that. Now, in reverse, for the second example here, the second exercise, they're giving us a set that's already expressed in set builder notation, and we want to try to think through what numbers are in this set. All right, so let's try to read through what this set builder notation is saying. This is saying the set of all x in the set of integers. So we want the set of all integers, x. The colon means such that. And then this last phrase here is essentially saying there exists a natural number n. There exists a natural number n satisfying that x is equal to 2n plus 1. And hopefully this sort of x equals 2n plus 1 is ringing a bell from Math 180. Essentially what this means is that we're looking for an odd integer. Not only is it an odd integer though, but there has to be a natural number n that satisfies this. And our natural numbers are all positive, right? And so essentially x is going to be odd, but also is going to have to be positive. Actually, if we try and think through this really carefully and look at some specific examples here, when n is equal to 1, x would be equal to 2 times 1 plus 1, which is 3. So that means the integer 3 is going to be in this set. When n is equal to 2, we're going to have x is equal to 2 times 2 plus 1, which is 5, so 5 is in this set. When n is equal to 3, we'll have x is equal to 2 times 3 plus 1, which is 7, so 7 is in this set, and we see that this is just going to keep going. As we increase our value of n, of our natural number, the x value is just going to be the next odd number in line, and it starts at 3 rather than starting at 1. Greater than 1. Because we can't plug in n equals 0 because 0 is not a natural number. All right, so this set just ends up being all of the odd integers that are positive and that are greater than 1. Well, this is an infinite set. There's infinitely many such integers, and so I'm just going to use that ... to indicate that this pattern is going to keep going. Okay, so we also want to define what a subset is. So we say that a set A is a subset of another set B, and we denote it using this notation here. A is a subset of B. If every element of A is also an element of B. So we can express this sort of using logical notation by saying for every x, if x is an element of the first set, then x is an element of the second set. So we could write that as x is an element of A implies x is an element of B. Right, so this is our sort of logical notation way of describing this. Okay. As a few examples, if A is a set containing 2 and 3, B is a set containing 2, 3, and 4, then we can say that A is a subset of B because every element of A, namely 2 and 3, are also elements of B, 2 and 3. Right, so B, the second set, the larger set, can have extra elements as well. But it doesn't necessarily have to, as we'll see in a future example. All right. The second question is asking, is the set of natural numbers a subset of the integers? Well, remember, the set of natural numbers, those are our positive whole numbers. And our set of integers is positive, negative whole numbers, and 0. So we need to check, is every element of the first set also an element of the second set? Well, 1 is also an element of the integers, 2 is also an element of the integers, 3 is going to be an element of the integers, etc. So this is going to be true as well. So yes, the natural numbers are a subset of the integers. Finally, is the empty set a subset of the natural numbers? All right, well, remember, the empty set is a set that has no elements. We can describe it as curly brackets with nothing inside. And the natural numbers are positive whole numbers. So to check that one set is a subset of another, we want to check that every element of the first set is also an element of the second set. There's sort of nothing to check here because there are no elements in this set. And so we would say that it's kind of vacuously true that every element of the first set is an element of the second set because there's no elements to check. So this is actually going to be a yes. And in fact, for the same reason, the empty set is a subset of every single other set. This is an important fact to keep in mind. Empty set is a subset of every set that ever existed. If you're not convinced by this argument for why the empty set is a subset of the natural numbers or any other set, another way to think about it is to look at it this way. So if we wanted to show that some set A is not a subset of B, we would need to find some element of the first set X that's not going to be such that X is not an element of the second set. We would need to find something in this first set that's not in the second set. You're never going to be able to do that with the empty set because there are no elements of the empty set. There are no X's that would satisfy this statement. So you'll never be able to show that the empty set is not a subset of another set. Therefore, the empty set is a subset of everything. We would say that two sets are equal. We've already talked about this a little bit, but if they have the exact same elements, which is like saying if A is a subset of B and B is a subset of A, then A and B are equal. Logically, we could write that by saying, well, using what we did on the last page, this is like saying for every X, if X is an element of A, then X is an element of B. That's what it means to say A is a subset of B. And for every Y, if Y is an element of B, then Y is an element of A. Right, so this is just another way of saying A is a subset of B and B is a subset of A. We would say A is a proper subset of B, and we denote that with a similar symbol but without the line underneath. If A is a subset of B, but they're not equal. In other words, if B has at least one element that's not in A. Okay, and so we could say, we had said in the last page that the natural numbers is a subset of Z, but we can get more specific than that and say, actually the natural numbers is a proper subset of Z as well, and that's because, here are the two things you need to check to see that they're a proper subset. N is a subset of Z. Every element of the natural numbers is also an element of the integers. But then we can also show that the two sets are not equal. N is not equal to Z. And that's because, for example, we can find an element of the integers that's not an element of the natural numbers. As an example, because 0 or -1 or any negative integer is an element of the integers, but not an element of the natural numbers. Okay, so to be a proper subset, you first have to be a subset, but you also have to have the additional property that the second set is in some sense larger. It has at least one extra element that the first set doesn't have. And now finally, the last thing we want to talk about for subsets is the power set, and this is going to be really important in this class. The set containing all subsets of a particular set A is called the power set of A, and we use this notation of a sort of script P of A to say the power set of A. To give you an example, if A is the set containing the numbers 1 and 2, then the power set of A is just a set of all subsets of A. So it's a set itself, and it's a set whose elements are the subsets of A. So we want to think to ourselves, what are the subsets of the set A? Well, you could have just the set containing 1, that's going to be a subset of A. Just the set containing 2 is also a subset of A. Are there others? Well, technically, the set A itself, right, the set containing 1 and 2 is a subset of A, because every element of this set is also an element of A, right? Any set is a subset of itself. And then finally, we had said this before, the empty set is a subset of everything. But these are the only subsets of A, and so the power set is just the set containing these 4 sets, right? The set containing 1, 2, 1, 2, and the empty set. It can get really tedious to describe the power set because that's a lot of curly brackets, and you can imagine that if A is bigger, the power set's going to be larger as well. And so sometimes it's useful to use what we call a bit string to encode a subset of some other finite set. So I'm going to give you an example here. If we let A be the set, this time we're going to call A this set here, consisting of 1, 2, 3, and 4. We can encode any subset of A by using a binary string, that's a string of zeros and ones of length 4, where a 0 indicates that a particular element is not in the set, and a 1 indicates that it is in the set. Okay? So if we wanted to encode the subset 1, 2, 4, which is indeed a subset of A, we have 4 spots to fill, and in each case we're going to put a 1 if an element is in the subset, and a 0 if it's not in the subset. So the number 1 is in the subset, so I'll put a 1 in the first spot. The number 2 is in the subset, so I'll put a 1 in the second spot. 3 is not in the subset, so I'm going to put a 0 in the third spot, and 4 is in this subset, so I'm going to put a 1 in the last spot. So the subset 1, 2, 4 corresponds to the binary string 1, 1, 0, 1. What binary string corresponds to the subset 2? Well, this contains a 2, but it doesn't contain a 1, a 3, or a 4. So this would correspond to the binary string 0, 1, 0, 0. And what would correspond to the empty set? Well, this contains none of the elements. So this is saying I don't want a 1 or a 2 or a 3 or a 4. So that would be the binary string 0, 0, 0, 0. And we could go backwards as well. If I, for example, took the binary string 1, 0, 0, 1, that's going to correspond to the subset which contains, let's see, we have a 1 in the 1 spot and the 4 spot. So it would correspond to the subset 1, 4. Now, the reason that this is going to be useful for us going forward is that we'll be able to have a better idea of how to count the total number of subsets of a larger